at Microchip. Just close this. Give me a second. Okay. So my today's presentation, I'm going to be talking about GaN on silicon carbide RF solutions enabling megatrends in 5G satellite communication, aerospace and defense applications. So the agenda for today, in the first section, I'll cover RF applications, which all have a need for beamforming. Then talk about the different types of phased array beamforming architectures, from analog beamforming, digital beamforming, hybrid beamforming, along with metamaterial beamforming, explaining the trade-offs between them. Then I'll follow up with some RF frequencies and some key RF front-end requirements for different applications. And then the second section will focus on SWaP-C, or size, weight, power, and cost impact, and the benefits of GaN on silicon carbide providing high linearity solutions for 5G, satellite communication, and space applications. So let's start off with looking at some of these applications we all are so familiar with. So just a quick recap: satellite communication, which is growing in a big way with low Earth orbit and geosynchronous communication operating in the K-band from 12 to 40 gigahertz. Now everybody's familiar with Starlink, with thousands of low Earth orbit satellites circling the Earth and providing broadband internet connectivity, along with other services using phased array beamforming. Then if you look at 5G, there's 5G fixed wireless access, there's 5G infrastructure with devices like small cells, femtocells, picocells, repeaters, all using millimeter wave beamforming. If you look at aerospace and defense applications, there are different types of radar systems that are used by aircrafts to monitor the radar environment, to alert the pilot of any hostile or foreign activity using active electronically scanned array radars, or AESA radars, in which a beam of radio waves can be electronically steered to point in a different direction without moving the antenna. All these phased array beamforming applications are looking at smaller size, weight, reduced power consumption, and better linearity solutions, which is what would be covered in this course of this next 30-odd minutes. Let's start off with looking at beamforming architectures. So everybody's familiar with the different types of beamforming, from analog beamforming, digital, to hybrid. So just a quick recap of what the differences are between the two and what the trade-offs are as we go into the talk. For any phased array, the ideal separation between the elements is the wavelength lambda divided by 2. So the block diagram shows analog beamforming. There are 4 phased array elements separated by a distance lambda by 2. So for as an example, for a 30 gigahertz signal, it will be a 5 millimeter separation between the phased array elements. In analog beamforming, the phase shifter does the beamforming by changing phase to do constructive interference for receiving and transmitting the signal by focusing the energy of the signal from the beam in a particular direction. So what's critical is this is all done in RF domain, RF frequency, hence is most sensitive to interconnect losses. Then the signal from the phase shifter goes to the power combiner splitter, followed by up-down converter and ADC DAC to the baseband. So in this case, for n phased array elements, there is only one digital front end. As you can see in the block diagram on the slide, for 4 phased array elements, there's only one digital front end comprising the ADC and DAC. The benefit of this architecture is the smallest number of components, lowest power dissipation. However, as the phase shifting is done in RF bands, this type of beamforming architecture is most sensitive to interconnect losses and complexity in phase shifting. The front-end module, comprising of the switch, LNA, phase and amplitude controller at the receiver, and phase shifter, PA, and switch at the transmitter, is shown in yellow in the slide. Now, how does this compare to digital beamforming? In digital beamforming, does the traditional up-down conversion to the baseband and digital phase shifting is done. The benefit of this architecture is it provides more precision as digital beamforming is done in the baseband. However, there is ADC DAC for each phased array, resulting in a large number of components and high power dissipation. In this case, for n phased array elements, there are n digital front ends. As you can see in the block diagram on the slide, for 4 phased array elements, there are 4 digital front ends comprising ADCs and DACs. Now, there's another type of beamforming, which is hybrid beamforming, which combines digital and analog beamforming to get the efficiency of analog beamforming with less number of elements, power dissipation, and precision of digital beamforming. As you can see in the block diagram, there are 4 phased array elements. There are 2 digital front ends comprising ADC DACs. If you compare to analog beamforming, there was only a single digital front end. And compared to digital beamforming, there were 4 digital front ends. So definitely, it's an optimal solution providing for larger arrays where you can optimize on the number of components and precision with hybrid beamforming. So far, we have looked at different architectures for traditional phased arrays along with the trade-offs. Metamaterial beamforming is another type of beamforming which is used in 5G, satellite communication, and radar applications. In this metamaterial beamforming, varactors are the tuning elements used to stir the beam. In traditional phased array beamforming, each phased array element is connected to the front-end module comprising of the switch, LNA, and phase and amplitude controller at the receiver and phase shifter PA and switch at the transmitter. This contrasts with metamaterial beamforming, in which all the antenna elements are connected to a single transmitter or receiver through passive phase shifters. Varactors, which are the tuning element used to stir the beam for beamforming, and hence is passive beamforming. We now understand the different types of beamforming architectures with trade-offs. Now let's look at some key RF front-end requirements for these different beamforming applications. In satellite communication, we are receiving the signal from far away. So the key figure of merit is low LNA noise figure for the RF front-end. Gallium arsenide, gallium nitride on silicon carbide provides the lowest noise figure, resulting in better signal-to-noise ratio and improving the receiver's sensitivity. In 5G wireless infrastructure, power amplifier output power, linearity, and power added efficiency determine the beamforming phased array size. GaN on silicon carbide with the highest power density provides the best-in-class PA-PSAT, PAE, and linearity. High PA-PAE results in low power consumption, and you get high linear output power, minimizing distortions in the highly crowded RF spectrum. Now let's look at some of these RF frequencies used in these applications. Satellite communication for a LEO or low Earth orbit and geosynchronous communication operates in the Ku band, the K band, and the Ka band. Radars operate in the L band, which is 1 to 2 gigahertz for identify friend or foe application, distance measuring equipment applications, tracking and surveillance applications, and S band 2 to 4 gigahertz for selective response mode S applications, and for weather radar. X-band is 8 to 12 gigahertz, as you can see on the slide, and is used for weather radar, aircraft radar to detect weather turbulence, and military applications. C-band is 4 to 8 gigahertz and used for communication applications such as sub 7 gigahertz 5G. 5G millimeter wave, which provides the highest bandwidth and data rate, uses 24 gigahertz and higher frequency bands. RF applications are looking for swap-C, or size, weight, power, and cost benefits. The huge dish antenna that you see on the slide is being replaced with phased array antenna, needing smaller size components for integration. The phased array antenna is shown in the second picture. Lower weight components are needed to have more payload, less fuel consumption for the satellite. High RF power, which is linear with high P1 dB and IP3 to reduce distortion, and efficient with high PAE to minimize the heat dissipation. And achieving all these benefits in the RF components at low total operating costs, including manufacturing and component costs. So swap-C becomes exceptionally important for components that are used in these RF applications that I've discussed so far. GaN on silicon carbide, as Professor Asbeck mentioned earlier, has the highest power density to generate high linear efficient output power. GaN on silicon carbide power amplifiers can operate at high frequencies in the Ku band from 12 to 40 gigahertz for satellite communication and have broad bandwidths, high gain with better thermal properties, meeting the requirements of RF applications. These are some of the results on power amplifiers using gallium silicon carbide. The first graph shows the linear gain across frequency and output power levels for gallium silicon carbide power amplifiers. And the second graph shows the linear PAE across frequency and output power levels. Now let's look at the technology transition as we move from low frequency up to 3 gigahertz. LD-MOS provides the highest output power and is the technology of choice. Gallium arsenide provides output power up to 5 watts across a wide frequency band up to 100 gigahertz, as you see on the slide, and the preferred solution in this band. Gallium silicon carbide, with its highest power density, provides the highest output power at high frequencies, meeting the requirements for aerospace and defense, 5G, satellite communication applications with broad bandwidths, high gain with better thermal properties, and is the technology of choice for power amplifiers. So far, in the first section, we covered the RF applications, beamforming architecture trade-offs, and key requirements for these applications. Then we talked about technology transition between LD-MOS, from LD-MOS going all the way up to gallium silicon carbide. Now I'm going to move to the second section of my webinar, which will focus on 5G megatrends, enabling discussion on 5G network architecture, ERP or effective isotropic radiated power requirements mandated by FCC, 5G power amplifier requirements, where you will see gallium silicon carbide power amplifiers play a very important role, and solutions meeting the requirements for the different beamforming architectures that are used. So quick recap, this slide shows you the different frequency bands for 5G globally. Different countries have different bands for 5G millimeter wave. In the United States, 28 gigahertz was the first 5G millimeter wave band deployed, which is going to be followed by 39 gigahertz. China, which is late in the game for 5G millimeter wave, is in the process of deploying 5G millimeter wave in the 24.25 to 27.5 gigahertz band. Now, how does a 5G architecture look, right? So this slide shows you the 5G network architecture. It's composed of macro base stations and small cells. Macro base station is connected to the core network using millimeter wave backhaul or fiber optic links, as you see on the figure. Macro base stations can talk directly to the user equipment cell phone, or can talk to the small cells, which can talk to the user equipment mobile device, providing the last mile connectivity. There are picocells and femtocells, which provide the network connectivity inside office buildings, where the connection might be weak or which have high user density. Femtocells, which are typically user installed to improve coverage within a small vicinity, such as a home office or a dead zone within a building. Femtocells are designed to support only a handful of users and support few simultaneous calls. They have a very low output power, up to 0.2 watts, as you see on the table. Picocells offer greater capacities and coverage areas, supporting up to 100 users over a range of 300 meters. Picocells are frequently deployed indoors to improve poor wireless and cellular coverage within a building, such as an office floor or retail space. Picocells can be temporarily deployed in anticipation of high traffic within a limited area, such as a sporting event, but also they are installed as a permanent feature of a mobile network as part of a heterogeneous network, working in conjunction with the macro cells to provide uninterrupted coverage for end users. They have an output power of 2 watts. Now let's look at macro base stations, which are large base stations covering a large area greater than a kilometer and have output power up greater than 100 watts. This kind of summarizes how a 5G network architecture looks like. Now let's look at what are the requirements of 5G millimeter wave. The 5G millimeter wave effective isotropic radiated power requirements mandated by FCC, with the mobile power limited to 43 dBm or 20 watts ERP transmit power, and the base station transportable power with a maximum power of 55 dBm ERP. So these are some of the challenges that the base station designers have to design to meet the requirements. And then we'll discuss how gallium silicon carbide power amplifiers comes in placed, meeting the requirements for this. Before I do that, let's look at how metamaterial beamforming plays in this as well. So we discussed the differences in the last section. So basically, it's another type of beamforming which is used in 5G satellite communication and radar applications. Varactors are the tuning element in metamaterial beamforming and are used to steer the beam. In traditional phased array beamforming, each phased array element is connected to the front end. Here, in contrast, in metamaterial beamforming, all the antenna elements are connected to a single transmitter or receiver through passive phase shifters, varactors, which are the tuning element to steer the beam. So effectively, the number of components are significantly less in metamaterial beamforming, especially the more expensive components such as PAs, LNA switches. So in traditional phased array beamforming, there is one PA LNA switch for every phased array element, whereas here that is replaced by one varactor for every phased array element. And as you're aware, varactor is significantly lower cost. So it's the most cost-effective solution for beamforming with metamaterial beamforming or passive beamforming. And this is being actively deployed. We at Microchip have had solutions deployed for 5G metamaterial beamforming. So we offer our varactors for 5G. One of the varactors I'm mentioning is the MB3903P2010, which is in production and is used in this nice little custom premise equipment for 5G fixed millimeter wave fixed wireless. So it's a very cost-effective solution, and we also have a complete lineup. So this is just a quick pitch of some of our solutions. Now I'm going to move to the PA side. So for the power amplifier, I talked about the maximum transportable power being 55 dBm as mandated by the FCC. So let's look at a G0P design, base station design. So for 60 dBm transmit power, so effectively there are some losses. So taking into account, you design at slightly higher than what is permitted so that your actual output is within the permissible range. So if you look at 640 antenna array element, so the array gain would be 10 log of n, which is 26 dB. So effectively, for 60 dBm, you need to have 34 dBm output at the power amplifier. In addition, for 5G, what you need to meet is a linearity requirement, which is 17 dB ACLR. And the other key critical component is your, depending on the modulation scheme, whether it's 64 COM or 256 COM, you need to meet the EVM requirements of 8% and 3% respectively. The different frequencies are mentioned out here: 28 gigahertz, 39 gigahertz, and 47 gigahertz. So a single GaN power amplifier can meet these requirements with low power consumption, 25% PAE, using GaN on silicon carbide technology. And let's look at some of these solutions which meet these specs. So we at Microchip have an offering with ICP2840, which is our power amplifier using GaN on silicon carbide. It's a MMIC, and it has an output of 39.5 dBm. It has an efficiency of 22% and 25% at 22% at backoff, 25% at PSAT, and effectively a small signal gain of 22 dB. So with this, you can meet the requirements like you saw. The requirements that were needed for a base station in the example shown in the previous slide was 34 dBm. So you have some backoff from the PA PSAT. We have another device, which is our 5-watt device, which is 37 dBm, and that has even a higher PAE at 25%. And this we offer as both a package solution as well as in die form. We do have other power amplifiers as well, meeting diverse needs of our clients. So effectively, in the KU band, 12 to 18 gigahertz, we have solutions as high as 50 watts and as low as 8 watts. And then if you look at KA band, we do have solutions going all the way up till 20 watts in the 32 to 38 gigahertz band, 10 watts in the 28 to 31 gigahertz band, 5 watt in the 23 to 31 gigahertz band. So pretty wide band of offering in terms of our solutions. So so far, I've talked about the benefits that gallium silicon carbide provides in different solutions. So the last section talked about 5G. Now in this section, I'm going to talk about satellite communication megatrends with discussion on RF solutions for satellite communication and space applications, including new space trade-offs in the LEO, GEO, MEO satellite communication, followed by different components used in space applications, from commercial off-the-shelf components to radiation-tolerant components to radiation-hardened components. So let's start with new space. New space, what is new space? New space is the emergence of private space flight industry, spanning areas such as private launch companies, small satellite constellations, or suborbital tourisms. So it's like these days, you go from East Coast to West Coast of the United States in 6 hours. However, what the future would be that you could be going from San Francisco to Shanghai for a meeting, taking your space flight, and then effectively having the meeting, having lunch at Shanghai, and then being back in States to have dinner back at your home. So that's what's the potential of space flights. So it's still a lot in the future, but that's kind of the way we are heading right now. Right now, it's mostly going for tourism to start with, but let's say 10 years out the line, what I just stated might be true. So we'll see what the time says, but that's new space for you. So new space has a different design mindset. It's a shorter mission life, fraction of the traditional NASA goals. What's important is to determine the best way to achieve the mission goals in a safe, most cost-effective manner. Now, qualification requirements can vary by function. So you can use components from commercial off-the-shelf to radiation-tolerant components to radiation-hardened components, depending on exposure to the space environment. So just a quick recap on the different Earth orbits. As you see in the picture, LEO or low Earth orbit at a distance of less than 2,000 kilometers from Earth, spanning between 320 to 1,100 kilometers. MEO or medium Earth orbit is at a distance less than 12,000 kilometers, spanning 8,000 to 12,000 kilometers. And geosynchronous Earth orbit is at a distance of 35,800 kilometers away from the Earth. So these are satellite constellations in each Earth orbit. Let's look at what are the trade-offs between the different Earth orbits before we go a deep dive into satellite communication. So geosynchronous Earth orbit being 35,800 kilometers away from Earth, and each satellite covers a very large area. So satellites appear stationary to the observer, or they are stationary, so they move, and effectively 3 satellites are sufficient to provide coverage around the Earth with a stationary antenna. So that's the key benefit of geosynchronous communication. It's few fixed satellites, covers a very large area, and it's the drawback is it does have a high latency. Medium Earth orbit communication has lower latency, being less than 12,000 kilometers as compared to geosynchronous Earth orbit. And each satellite covers a larger area with 6 satellites sufficient to cover the entire Earth with slow tracking antenna. Now, low Earth orbit satellite communication has very low latency, being less than 2,000 kilometers away from Earth, and each satellite covers a very small area with hundreds and thousands of satellites needed to provide coverage around the Earth with a fast tracking phased array antenna. The advantage of LEO satellite communication is smaller, low power satellite constellations that can be batch launched, providing internet connectivity with low latency around the globe. The picture shows geosynchronous satellite, which is orbiting 35,800 kilometers away from the Earth, and LEO satellites orbiting less than 2,000 kilometers away. There are data gateways connecting to the satellite constellation, providing content and satellite communication with the customer premise equipment as user homes. So geosynchronous satellites have been providing connectivity in flights. So before the LEO satellites, when you were going on planes and doing internet connectivity on flights, that was all through geosynchronous satellites, airborne vehicles to the ground. So that's now with the low Earth orbit satellite constellations such as Starlink being deployed, there's an exponential growth with over of these LEO satellites with over 3,000 mass-produced satellites in the low Earth orbit. And Starlink, as an example, is providing over 1 million subscribers internet connectivity. So it's able to provide connectivity in areas which do not have internet connectivity, as well as connectivity globally with its constellation of satellites. Some of the bands for satellite communications are shown in the table. Earth stations transmit, the key takeaway is the Earth stations transmit the uplink signals to satellites at higher operating frequency, while satellites transmit at lower operating frequency to be cost effective. As we go to higher frequency bands such as Ku and Ka band, there is higher bandwidth available, resulting in higher data rates. At these higher frequencies, K band 12 to 40 gigahertz frequencies, there is attenuation due to rain, as well as expensive equipment is needed to transmit and receive the signals. This slide shows you the RF signal chain for satellite communication. Looking at the diagram from left-hand side, there is a downlink signal from the satellite received at the ground terminal, which is selected using a bandpass filter or a diplexer. This signal is very small as it is being received from the satellite and is amplified using a low noise amplifier, then down converted from the RF frequency to baseband using a mixer for signal processing. Some of the other components in the RF signal chain are filter banks, switches to select the RF signal, variable attenuators for signal conditioning, phase frequency detectors, prescalers to generate local oscillators, PLL frequency to transform the signal from RF to baseband. So that was on the receive side. On the transmit side, the baseband signal is up converted to RF frequency using a mixer and is amplified using a power amplifier to generate large output signal at RF frequency, which is then transmitted to the satellite as an uplink signal. So now we look at some figures of merit used in components in the RF signal chain that we just saw. The figure of merit for power amplifier at the transmitter is to generate high linear efficient output power. The linearity is determined by IP3 and P1 dB. The higher the IP3 and P1 dB implies higher linearity of the power amplifiers, which results in low distortion of the RF signal output, causing less interference. Power amplifier efficiency is determined by the PAE, or which is measured in percentage. Efficient power is generated with higher power amplifier PAE. Now, at the receiver, low noise amplifier noise figure determines the sensitivity of the receiver with lower noise figure, resulting in better signal sensitivity and improved range. For RF switches, the key figure of merit is insertion loss and isolation. The insertion loss should be as small as possible to prevent losses in the RF signal chain, and isolation between the ports of the switch should be high to minimize leakage between the RF ports. Then for prescalers, phase noise at dBc at kilohertz offset is the key parameter, with low noise floor improvising the range. Now, reliability is very critical for space applications. So the key NASA EEE-INST-002 specifies the reliability standard for electronic, electrical, electromechanical components, which is dependent on mission. So it's critical for critical mission length. And in terms of packaging, it's plastic integrated circuits with radiation hardened components. So effectively selecting the component based on the most cost-effective radiation tolerant option available to meet the mission goals is kind of what is the essence. So now let's look at the COTS, or commercial off-the-shelf, versus radiation-hardened versus radiation-tolerant components, and what are the key requirements for these as we go to new space. With new space, a shorter mission life, component selection has become extremely critical to achieve the mission goals of safety in the most cost-effective manner. So component selection can vary by function from COTS to Rad Hard to Rad Tall, depending on exposure to space environment. Gallium silicon carbide and gallium arsenide components can be screened for radiation tolerant or radiation hardened requirements because of the inherent nature of these processes. COTS components are typically industrial temperature range and have radiation tolerance under 1 kRad SI and are less expensive, whereas radiation tolerant components can be characterized for radiation tolerance up till from 50 to 50 kRad SI and have higher costs. Radiation hardened components have radiation tolerance over 100 kRad SI and are significantly more expensive. So these are some of the trade-offs between the three different types of components available. Now I'm going to spend a couple of minutes talking about some microchip solutions for space applications, which include power amplifiers, low noise amplifiers. So we offer commercial off-the-shelf components for all of these MMICs, but because of the nature of these power gallium arsenide and gallium nitride, all of our COTS components can be screened to be Rad Hard or Rad Tall. So gas HEMT transistors and gallium silicon carbide are developed processes capable of being screened. The components can be screened per mil 38534 or the NASA EEE-INST-002, or even to a specific requirement that you might have. We offer these solutions in die form. We also offer it as plastic package as well as in hermetically sealed packages. So quite a lot of offering that we have both for ground terminals, which we offer commercial off the shelf, and then for space applications where we offer solutions where we can do the screening to meet the requirements per the different screening specifications. We also have the diodes as well, which are developed on processes with space heritage. So we have a lot of our products which are already in space. We can screen these to MIL 750, 883, 19500, 38534. We can also screen them to the ESA ESC C5010 or a customer required specification. We also offer SAW products. So we have SAW filters as well as voltage controlled SAW oscillators. We have over 40 plus years of space heritage with components in space in various applications, from RF switching, communication data links, SAW filters, VCSOs, as you see on the slide. So just to summarize our offering for space, diodes and SAW products are developed in processes with space heritage. Gas, gallium silicon carbide MMICs, transistors are developed in processes which are capable of being screened up to Rad Hard. Space screening per mil 38534 or EEE-INST-002 or any customer provided specification can be done. We offer hermetic seed packages for MMICs, transistors, diodes, SAW products. And to summarize, we have RF solutions from COTS to Rad Hard, plastic to hermetic seed packages for space applications. So my final section of my webinar or talk will focus on RF solutions for aerospace and defense. Relatively, it'll be a quick section. For aerospace and defense, the different types of radars are there, from radars for ship, air, weather, marine, jets, and a lot of these radars are going into transition into AESA or active electronic associated arrays. So that's a great inflection point in which a lot of new designs are happening in the space. If you look at the radar systems, the key components for radar systems are the power amplifiers, the diodes or the pin diodes, which enable protection of any jamming signal, the low noise amplifiers of the receiver, SAW filters, which enable signal to be filtered, mixers for up and down conversion, frequency converters. So this is an example of a block diagram of a radar system. So as you see from the left-hand side, there's an antenna where and then where you can transmit and receive the signal. Then you have a switch to for transmit receive, and then at the receiver you have a limited diode. The limited diode enables you to effectively the limited diode enables you to prevent any jamming signal to destroy your downstream devices. Then you move on to your low noise amplifiers. The low noise amplifier and SAW filters. The purpose of SAW filter is to filter out your desired signal of interest. And then you have your low noise amplifier, which enables you to have the lowest noise figure so that you can extract the signal and then amplify it. Then on the transmit side, and then you down convert it to baseband and then do the processing using the FPGA. Now on the transmit side, your baseband signal gets up converted using mixer, and then effectively you take out the signal of interest, amplify it, and then using a high power amplifier, which is typically used on GaN silicon carbide, you can multiply it at a higher output power to get the desired signals for the radar. So that's kind of your radar system. And then here, GaN silicon carbide plays a pretty important role in terms of the transmitter to provide the high output power, and gallium arsenide for the receiver LNA. Same thing with electronic warfare, ECM. This is a receiver diagram. The earlier one was a transceiver diagram, but all the different components are shown out here, from phase frequency detectors, pin diodes, MMIC switches. So just to end the webinar, a couple of slides on our offerings. So effectively, we do offer the MMICs that we talked about, that I talked about earlier. Then we also have transistors, and these are transistors which go all the way up to 100 watts of output power. We had MMICs using GaN silicon carbide, which went all the way up to 50 watt of output power. Now transistors go up to 100 watts, so you see the difference. We have an offering which has different frequencies. We offer a nonlinear transistor models, which enable you to get the best-in-class performance from your designs. So Keysight ADS nonlinear models are available. These are all our GaN silicon carbide MMICs. So these are, as you can see, the key. It's a pretty broad portfolio, and we offer devices in the frequency range from 2 gigahertz to 18 gigahertz, all the way up to 38 gigahertz. And then we have band specific, right? If you need X-band, 7.9 to 11 gigahertz. If you need AKU band, it's like 28, 40, 27 to 31 gigahertz. And we offer these solutions both in the die form as well as in the package form. The different versions are shown you. You'll have a copy of the presentation for your reference. So I think in summary, what I would like to conclude my the talk is that GaN silicon carbide provides an essential solution for power amplifiers with all the benefits, and this kind of showcases microchip offering in terms of providing a complete RF signal chain solution from the PAs using GaN silicon carbide. Then we do have low noise amplifiers using our gallium arsenide technology. We have pin diodes, which can be used as limiters or switches. We do have RF switches, MMICs as well, phase frequency detectors, prescalers. So effectively, the benefit of the solution is that your entire RF signal chain can be done using components made. So we provide the entire signal chain solution, and we kind of enabling. So just to summarize my talk, so with the huge gallium arsenide, GaN silicon carbide MMICs, HEMT transistors portfolio with best-in-class RF performance, we are enabling the megatrends in 5G satellite communication, aerospace and defense applications, as I showcased with the applications in my talk. The MMIC HEMT transistors have flat gain across the band, excellent noise figure and linearity. The benefits of GaN silicon carbide technology is high power density, high efficiency, high switching speeds, low latency, and then providing you swap C benefits. For RF solutions for space, GaN MMIC transistors are development processes which are capable of being screened all the way up to Rad Hard. When for diodes, we have a complete portfolio of integrated and wideband parts for each signal application. For SAW products with PCSOs, temperature compensated, as well as SAW filters, we are providing the next level of RF performance, completing the RF signal chain solution. So I think that's all I had. Thank you for your time today. I appreciate it. Back to you.
Thank you so much, Mr. Chandok. That was very, very informative talk. And thank you for explaining the future trends in 5G, SatCom, aerospace and defense, and all that market. We have time for one question. And from the chat, I'm going to pick a question on metamaterial. So the question is, how real-time beam steering is achieved using metamaterial-based phase array? And can it achieve scanning and steering in nanoscale on par with 5G?
Yeah, no, I think that's a great question. So metamaterial beamforming effectively is currently being used in fixed wireless, 5G fixed wireless access. I mean, there are products which are in production, and then they're meeting the requirements for 5G fixed wireless. And effectively, you are able to stir the beam and able to receive the signal. And effectively, it depends on your array size. So what I have seen in production is array sizes as large as